I'm oral historian Mike Chappell. Today, June 15, 2008, I'm interviewing Dr. John Potts for the Endocrine Society at its annual meeting being held this year at the Moscone Center in San Francisco. Dr. Potts is a past president of the Endocrine Society and is a member of the National Academy of Sciences and of the Institute of Medicine. Dr. Potts has been a pioneer in parathyroid hormone for over 40 years. His fundamental contributions resulting ultimately in FDA approval of parathyroid hormone therapy for the treatment of osteoporosis. Currently, Dr. Potts is the Jackson Distinguished Professor of Clinical Medicine at Harvard Medical School. Dr. Potts, please tell me a little bit about your family background, starting with your grandparents.
Oh, well, very interesting. My mother's parents were born in Ireland, and my father's parents were of English extraction but lived for a long time in the United States, back actually to Revolutionary War days. So my paternal grandfather was a florist and a very distinguished sort of grower of rare plants and had a very successful business in the little town I grew up in. And they were Episcopalian. And my mother's family were Irish Catholics, and they were born in Ireland and came here probably in the early part of the last century. And though the two clans, as it were, met in quite harmonious results, and at least as far as I was concerned, and had one sister, and lived in that small town of Morristown, New Jersey, which is a rather lovely little town in the orbit of Philadelphia.
What kind of education did your parents have?
Well, both my parents went to high school. My father went to a sort of abbreviated program in business school, and my mother, I think, did some work after high school, but neither had a college education. But as with many immigrant families, or recent immigrants, you might say, they valued education and intellectual values and sort of pushed my sister and I along, as many families did in those days. And so I went on to college and medical school, obviously.
What did your mother and father do for a living when you were growing up?
Well, my father was also a florist, and was quite successful. And so when I went to college and medical school, they put me through, and I didn't have to work. I did work in the summers, but they supported me very well. The idea was that I should try to do well in school, and their job would be to support me. Pretty good bargain.
What was it like growing up at the end of the Depression and during World War II in a town with a Quaker heritage?
Well, we didn't, we knew about the Quaker heritage, but it didn't directly impact on us very much. It was a very good friends school there. I think that my father's family did quite well despite the Depression. The florists were not as affected, so I think they were mindful of this, but I didn't feel any direct impact of that in growing up. I guess, I was 9 when World War II began, and of course, by that point, the agony of the Depression, I was born in 1932, it already eased quite a bit, but I don't think we felt it as many people did living in cities. A small town was a lot easier, I think.
Was education a priority in your family?
As I mentioned, it was very important to them, and that's why they encouraged me to excel at school, and they would take care of supporting me. I didn't have to work nights and things like that. It was a very good bargain, I thought.
What kind of a student were you?
I did pretty well. I did pretty well. I was sort of top of my class all along.
Were you making any decisions at this point about what you might want to be doing when you were grown?
Well, somewhere along the way, the idea of becoming a physician, I think probably reinforced by my mother, came in my mind. I don't remember when exactly that happened, but by the time I was in college, I was definitely heading in the direction of medical school.
How did your mother encourage you?
I don't remember. I mean, it just, I just remember thinking that, I remember our talking about it, what it would be like to be a physician, and I don't remember any eureka moment. It was just reinforced in the way that parents often do a good job.
And then you went to Lasalle High School and college.
Yes.
And why did you go to Lasalle College?
Well, you know, I think my horizons weren't that broad. I would think it was a fine choice for me, as it turned out, but I didn't think about going to the Ivy League schools and things like that. It wasn't, as I had already mentioned, there wasn't a long tradition of family involvement with college education for themselves. So if you're busy doing what you're, trying to grow and learn, your orbit of awareness may be not so great. And if you come from a background where many people have gone to college, as my children, for example, one went to Brown and one went to Yale and one went to Harvard, they would think very, very differently about what the options might be. I was quite content with it and enjoyed Lasalle College. I had my greatest teacher that I ever had was at the college. And then for medical school, I knew that the University of Pennsylvania was very distinguished, and that's where I wanted to go.
I wanted to ask you, are any of your children in science or medicine?
Yes, my daughter is a physician, and she's an assistant professor at Harvard, and she's at Children's Hospital in Philadelphia. Philadelphia, in Boston, and where she grew up. And my son-in-law, her husband, is a physician also. That's how they met, through that mutual interest in medicine, really. She was much younger. And he was the head of cardiology at the MGH and professor at Harvard. And he now works as the head of worldwide research for Novartis. That's the only medical connection. My other son is sort of interested in a lot of things, and my youngest son is an architect with a firm in Philadelphia.
You mentioned that one of your greatest mentors was that?
Yes, it was a teacher, Claude Cook, who was an ex-Marine, but a very sensitive soul and a wonderful poet and just a born teacher. And we became so excited by his style of teaching and his introduction to great literature of the late 19th century and early 20th century that there were four of us who all were heading to medical school, and we spent a lot of time in special classes that he held. And in fact, after I went to medical school at the University of Pennsylvania, we used to go back to his home, which was in Germantown in Philadelphia, and there would be discussions about literature. And I went on right through almost all of my time at medical school. There's a little sketch that he made of me with the bottom. It's very interesting. Dr. John at the bottom, 1956. So that's the year before I graduated. So I know we must have been going back there pretty often. He was very inspiring, with a very low-key style and a depth of knowledge and excitement about great concepts in literature, and also trying to relate the literature of the time to what was going on in other fields in the arts, in painting and sculpture and music. He was a very cultured person.
And science and medicine, too? Was that part of that?
No, he wasn't interested in that at all. He knew we were going there, and he thought that was wonderful. But he wanted to humanize us, was his effort, I think.
Why did you choose the University of Pennsylvania Medical School?
Well, from the point of view of anyone living in the Philadelphia area, at least to my mind, it was the most distinguished with the old lineage. And at that time, there were several other medical schools, but none were part of a formal university. And so I really very much wanted to go there. And I didn't know what the competition would be like and whether I would be successful in getting there or not. And so I'd done very well in college, and I was sort of, along with another friend of mine who also went to University of Pennsylvania. We were sort of the two that were at the top of our class, I guess, by grade point average. And when it was complicated because you were supposed to apply to various medical schools, you don't know who's going to accept you. And they had many applicants. It's always been the case with medical school. It's a complex process. So I didn't know whether to apply to the other schools, because if they gave you an application, gave you an acceptance, you had to take it or drop it. And University of Pennsylvania was always the last one to do this. So I had my interview, I remember, with the dean of the medical school there, and we had a nice chat. And at the end I explained this dilemma to him. And I said, I haven't applied to the other schools yet because I don't want to be losing my other options. He said, oh, you haven't applied anywhere else. Well, if I were you, I wouldn't. which is the closest one could get to knowledge that it was going to be fine. So that's why I followed his advice and went there. Very kind of him.
What feature or features mark your medical school training?
Well, that's the time when I became very interested in science. Not at the beginning. I mentioned that I was still going back to Lasalle College, the teacher that I'd had, and we enjoyed him very much. And I worked reasonably hard, but I thought I was going to go into the practice of medicine, maybe back in my hometown. And it wasn't that difficult to work at a reasonable but not blistering pace, so to speak. And I knew I wasn't in the top 1 or 2 of the class academically, but I was enjoying medicine, found it very interesting. And then when I got to the 3rd year of medicine, when you begin to see patients as a student, I became very interested in the science that lay beneath the problems that we saw in patients. And I became very interested in science at that point, having seen others who were in my medical school class who'd been interested in science from an earlier time and had done work as high school or college students. I hadn't, but then I suddenly wanted to. And I knew there was a way to get into that, to go to a good academic residency training program where medicine and science were both important values, let's say, like the Massachusetts General Hospital, which I learned about in those days. And I was disappointed because I thought, well, you've been cruising along here, you have another barrier or hurdle to overcome, and you haven't been running fast enough. But to my great surprise, I hadn't done as badly in school as I thought. And when I applied the following year to the Massachusetts General Hospital, they actually accepted me, which was very exciting for me. And part of that drive in that direction was reinforced by another wonderful supporter and mentor, a surgeon called Brooke Roberts, who was a very distinguished Philadelphian from a long lineage, but he had a gift for encouraging young people, and he was interested in parathyroid hormone, and he did a lot. Well, he was interested in sort of the metabolic problems, and particularly parathyroid disorders. And I actually wrote a little paper with him about that. And I'd been interested in parathyroid hormone for some reason, thinking about science, endocrinology, and the idea that there would be a servo system, like a beautifully modulated thermostat that would keep a particular regulated variable at a constant level by turning on and off to raise or lower it, was fascinating to me. And so I became interested in parathyroid hormone, and maybe the fact that I'd spent a bit more time and written a small clinical paper and so on. I did it because it was exciting, but it turned out to have probably been helpful in getting into the next step into the residency that I went to.
So it was your relationship with Dr. Roberts that sparked your interest in endocrinology and...
In part. Partly it was intrinsic reading about things, taking classes at that time, and partly reinforced by him.
Okay. And before that, your idea of what you were going to be, the type of physician you were going to be?
Would be a practitioner in a town like the people that I knew that had been my physicians. So that 3rd year really changed my course.
What was the dominant paradigm or model of the parathyroid when you began to enter into the thinking about it?
Well, it was known, as I think I've just described it, as obviously a very subtly, beautifully regulated servo system that would turn on and off. It was known there were glands and they produced the hormone, and the blood calcium was what they regulated, and they would keep the calcium constant no matter whether you were eating calcium or deprived of calcium. It always stayed absolutely steady, which we knew was important to health, and low or high levels of calcium could be destructive. In fact, very low calcium could be fatal. So we knew that, but the nature of the hormone was known by then that it was probably a polypeptide. You know, it was not like a steroid hormone. It was made of amino acids together in a peptide chain. But it wasn't purified, and it was very hard to know exactly what to do next to be able to measure it in blood, etc. That got me sort of interested. I became interested in that.
Did you have a particular research goal in mind then at this point? How you were going to?
No, I think I was young and didn't have a lot of background. I just thought that would be an interesting area to work on if I have an opportunity to do so. But as an intern and resident in medicine at the Massachusetts General, where I had gone by then in Boston, my job was to take care of patients and learn how to be a good doctor. And I did learn early on that there was then the opportunity of going to the National Institutes of Health, which was becoming a great beacon for people. And if they were interested in medicine and science and biomedical research, if they went in a strong academic residency program on the one hand, then they might have a chance to go to the NIH where they could learn science in a way that would allow you to begin to formulate a plan about what you might like to do.
What initially got you into your position at the NIH?
Well, I think the people that I worked with at the MGH took a kindly attitude toward me, and I suspect that Brooke Roberts wrote letters, probably wrote a letter, and they thought Alex Leaf, who was later to become the chief of medicine, felt that I was interested in science, and so I think he wrote a strong letter, and several other people. I don't know, since you never see those letters, but all I knew is that I was very excited one day to be called and be told that I was accepted in the National Heart Institute.
And who was your mentor at the NIH?
Well, when I went there, you had a few months to pick the investigator you wanted to work with. And I learned that there was a fine protein chemist named Christian B. Anfinsen, who was at that time applying the techniques of protein chemistry at a stage when it was still a very young field. And that I had heard that he was very receptive to physicians with very little training, but who were enthusiastic and supposedly reasonably bright, and he would bring them in and show them how to work in science. And so I applied to him, and he took me. It was very nice. The NIH had a system where you would have 6 residents chosen from different institutions around the country would go into the Heart Institute. Other institutes had similar tracks. There was something called a research associate. If you'd done a lot of research, you might have gone directly into research. If you looked like you had potential for it, you would do 1 year of a sort of residency, helping to take care of the patients that were admitted to the clinical center, but then would go on and do your research. So I applied to him, and he was gracious enough to take me in, and then I plunged into the world of protein chemistry, which was very exciting.
What research were you doing in protein chemistry?
He was working then on the structure of an enzyme called pancreatic ribonuclease. It was an enzyme that for today isn't that important, but it was available in large amounts and could be purified, and the techniques for doing the structure of a protein were still very laborious, required lots of material, and the methods had not been developed in a sophisticated way that came later. So you had to have something that was in large quantity. The first molecule that structure was done was insulin by Frederick Sanger, who was in the MRC at England, and he had laboriously worked out the structure of insulin, and ribonuclease was one of the next important ones being worked on. And Anfinsen was a real pioneer in the field, and he adapted the techniques of protein chemistry and also a lot of ideas about how a protein organizes itself. Because ribonuclease, bovine pancreatic ribonuclease, was a highly organized enzyme. The chain was folded back on itself and stabilized with disulfide bonds, and that's what made it what it was. And part of the reason he later won the Nobel Prize was he not only did the structure of this along with 2 people from the Rockefeller who were independent, really competitors, but he also inaugurated the concept that the primary structure of a protein determines how it folds itself, which was a very important concept. So I worked on that and wrote 3 or 4 papers in that area.
How did this relate to your interest in the parathyroid?
Well, it meant that I'd learned now the tools of how to do it. I could get my hands on the parathyroid hormone, and I thought that was a rather formidable task, and I hadn't done very much reading then. And I went to visit Howard Rasmussen, who I knew had already started some work in this area. He didn't really encourage me very much, I would say. He was then at the Rockefeller. But then I learned from another colleague, just as I was in the middle of my early phase at the NIH, that Gerald Auerbach, whom I'd heard of, had also come, like me, to the NIH from Tufts. And he was a person who I knew had just recently developed a new technique for purifying parathyroid hormone. So we met at lunch and decided to collaborate, and that began a wonderful collaboration that lasted for over a decade, even after I subsequently left NIH. I was there from 59 to 68, and beginning in around 1960, began to work hard on it with Auerbach on parathyroid hormone. And Donald Fredriksen, who was the head of one of the laboratories, gave me an opportunity to have my own laboratory, to stay on. You didn't necessarily have that opportunity. They were there for 2 years, then you would leave. So I stayed there altogether for 8 years and had a little section on polypeptide hormones.
What was Donald Fredriksen like what was his style as a leader?
Well, he was a very charismatic and interesting person who took a lot of interest in the residents. And we used to meet with him periodically, and he would talk about what was going on in the broad area of metabolic disease, which was his interest. He was interested in lipoproteins. And he, like a lot of the early mentors, Bob Berliner, who was the director of intramural research, and Fredriksen was the clinical director in the Heart Institute. Anthony was head of one of the laboratories. They all were very supportive of the young residents that were around, and it was great of him to give me this opportunity.
And what were your most significant contributions in the field at this time, in your NIH days?
Well, we'd learned how to isolate the material in high yield. We learned how to do the structure. We were moving very well in late 1960s when I was there. We had part of the structure worked out, but it was still very laborious and difficult because the amount of material available was very tiny compared to the amount of material you could get, say, with pancreatic ribonuclease, which was a byproduct of pancreas extracts from cattle. Now that's where the parathyroid hormone came from too, but there's much less of it in the body than there would be of pancreatic ribonuclease, which is a large enzyme dumped into the intestine to do its job. So it went slowly. Hugh Nile, who was a wonderful scientist, came from, a young scientist, younger than me, came from the laboratory of Dr. Per Edman in Australia, who just developed an automated technique for sequentially breaking off one amino acid after another in order to determine the order of the amino acids, which was, in the end, the structure. And so he joined us, and we began to use his techniques. We diverted, because at that time, the molecule calcitonin, which seemed to be the yang of the yin and yang of parathyroid hormone, calcitonin, became available, and we worked on the structure of several of those while we were building up the stockpile of parathyroid hormone. Then MGH invited me to come back as the chief of endocrinology. So we took the partially completed structure of the parathyroid hormone, continued to work with Auerbach, who remained in the Arthritis Institute, a different institute than I was in, and we continued to work on the material and exchange it, and by 1971 we had a good portion of the structure determined, at least at the business or amino-terminal end of the molecule. And there we then had the problem, if the structure was correct, the only way you prove a structure is to synthesize it. And another Australian had joined me, Jeff Tregear.
This is the MGH you're talking about?
No, this is now at the MGH. So the continuity of work went from NIH to MGH. And at MGH we did do solid phase synthesis, Tregear did, and the material was active, but in a bioassay that had been developed by Auerbach. And we were all very excited, and we had achieved the structure. We must have been correct because it was biologically active.
I want to ask you, before we leave the NIH, as far as developing your career and building a network, I want to talk about a network a little bit within the biomedical enterprise. What did you learn at the NIH?
Well, it's a very interesting question, how you build a network. I mean, I think it has to do with many different features, probably has to do with personality, good fortune, other young people that want to advance themselves. But I found myself building up a very nice group of associates, and I enjoyed them all and felt that this was a real opportunity to solve the problems, the research problems that I wanted to work on. And so I, by that time, had quite a few young people that had been working with me over the many years that I'd been there. And they seemed to enjoy working together, and we could accomplish a lot as a group. And when I went from NIH to MGH, I invited them to come with me, and we put in research grants and made it possible for them to go. So there was a sense that the laboratory had a certain harmonious interaction. I mean, everybody is worried about their own recognition, whether it be the leader of the lab or the youngest person in the laboratory. But if you can understand how to trade off those sensitivities so that everyone gets their moment in the sun relative to their experience and feels supported by one another, it can be a beautiful thing. It's one of the, it happens in other fields too, but in biomedical research, it's a beautiful thing when you see a lab that works together well. And the leader has to appreciate what that's all about and nurture it, and sometimes resolve conflicts or swallow his own reservations about something in order to keep the group going well.
When you mentioned moment in the sun and nurturing, it made me think of your family as growers.
Ah, yes. Well, I don't know that it would be a very nice analogy to draw out, but it might be a little forced. It was more the psychological aspects of it, I think. Some people are brilliant and great leaders of laboratories, and their sheer intellect is awesome. And sometimes they aren't the most supportive mentors, but they often develop very good laboratories because of the force of their intelligence and their drive and their position. And people go there and work because they will learn a great deal. Other groups are a little more built on, I think, a mutual support, a sense of helping everybody to work together. I mean, there are many ways to do this, but the one that I liked was the one that we did. Maybe it was because the sheer force of my intellect was not as great as some of the others. I'd better be nice to people. I don't think that was a conscious decision. Rather, I think the point was that I felt very fortunate to be in this position and to be able to making the progress that I could see toward the goal of understanding parathyroid hormone and producing the chemical side of the biology of the problem. And I could see that many people were contributing to this, and we could do things as a unit that we couldn't do, or as a group that we couldn't do by ourselves. I think that was what I actually felt about it. I don't believe you do these things because if you don't keep the people loyal to you, the work won't get done. That doesn't quite make sense. It's merely that as you rush for the goal, and you have people working with you, if you have enough sensitivity to see their needs and how to nurture their career development, the thing becomes a harmonious, gelled achievement of organization.
You were, your position at the MGH, your original position was chief of endocrinology in the endocrine unit?
Yeah, I was chief. There were several, traditionally at the MGH there had been two major units, a thyroid unit and the endocrine unit. And there was a great man who I never met because he was disabled by surgery, Fuller Albright, one of the great and imaginative investigators of the entire 20th century, who achieved many things despite severe physical disability from Parkinson's disease, which he acquired because of the influenza epidemic of 1918 when he'd volunteered as underage to get into the service, contracted influenza, and about 10 or 15 years later the disease began to manifest itself. But he continued to be creative right up until this accident to try to correct his surgical difficulty in 1957 left him totally paralytic and unable to speak. Anyway, after he had become disabled, it was necessary to find the next chief of endocrinology, and by that time the man who'd been the chief of the renal unit, Alexander Leaf, decided, and was very interested in science and people who were doing things that would bring science as well as medicine to bear, is the one who invited me to become the chief of the endocrine unit, which was a very big responsibility.
Could you sketch out the endocrine unit a little bit, what that...
Well, I mean, it turned out that I had to write my own grant to come. They didn't have a lot of funds to support me. There was partial salary support for me. So we had to produce the resources. And I had some research space is always a critical thing in a institution related to biomedical research. If you get some space, then you can build a group. If you don't have any space, it doesn't matter how many people would like to work with you or how good you are as a leader, you won't have much of a group, but you can't work in closets. So we did have the space, but we didn't have very much resources. We had to build that up on our own. I had to learn how to do that. So I once waggishly said to one of my colleagues a few years after I'd been there, and now I knew what it meant to become chief of the endocrine unit. You were given an empty hot dog concession stand, but it was in Yankee Stadium, so that if you knew what you were doing, you could begin to produce the resources. And so we had good luck with NIH. They liked what we were going to do, and they gave us a grant, and we got some support from industry and a bit of from another private foundation. And so over a few years, which all leaders of laboratories know, you have to find money different ways that will allow you to build up the support that you need, because you have young people that are working with you and they're depending on you. If you don't have the salary for them, you've failed them.
And the research you were doing, your own research at this point, you said this was a continuation of
what I'd done at NIH.
You're still operating within the
parathyroid hormone. In fact, I've stayed working
on the same paradigm?
Yeah, I've stayed working on parathyroid hormone my entire career, because the field of interest has magnified underneath the concept of parathyroid hormone, and we can talk about that later, but the level of interest, its application in medicine, what you want to understand, how it works, is probably somewhat analogous to other biologic systems. You begin with a limited set of questions. Can I get the structure of the hormone? Can I develop an assay to measure it? Can I learn more about how it works? And then gradually, as success comes, the complexity of the system in which it operates becomes more apparent. So the breadth of the question constantly grows. And if it's an important question, other people are working on it. For example, when we did the structure of the parathyroid hormone, a younger colleague who'd been with me at NIH but didn't come with us to Boston also worked independently on the structure, having learned the methodology that Niall brought to us. So he also did the structure of the hormone and continued to work on it independently. That was Brian Brewer, and he then later went into the lipid work with Donald Fredriksen. And didn't stay in the parathyroid hormone field, but as we did when we went to Boston. But we could get to that later. But I mean, the areas that we wanted to understand about parathyroid hormone kept growing. We had the hormone. Now then, molecular biology, the impact of molecular biology became apparent, and we wanted to develop, apply it. And Henry Cronenberg, who's now the chief of the unit, and others came to the unit, Joel Habener, and a group of other very talented younger people, and they learned the technique of molecular biology, not from me, but from other colleagues, where they went to, under the fellowship support that we had, they went to MIT, to the laboratory of Alex Rich and other people, and learned the molecular biology techniques, and then came back, and they were able to work on applying molecular biology techniques. So we then cloned the receptor. So now we had the lock and the key. The hormone is the key and the lock is the receptor, and we worked on that. And then later, I think I mentioned to you, perhaps I didn't, John Parsons, the pharmacologist, came. and we turned to a different direction. We'll get to that later, probably.
Well, no, this is what I want. This is what I'm asking you. Up until John Parsons arrived, would you say you were working within the dominant paradigm at that point, the homeostat?
Yes. I see what you're getting at. The point was that parathyroid hormone was thought of as the regulator of calcium metabolism. It would preserve calcium egress in the kidney. It would take calcium in, if you were in a period of starvation, it would take excess calcium from the bone. It would help vitamin D to absorb all the calcium that was available in the intestine, if any. And it was this servo system whose job was to control the blood level of calcium, period. If it did anything to the bone, it was best understood by seeing what happened when you had a small tumor of the parathyroid glands, overactive parathyroids called hyperparathyroidism. In that case, the bones had holes in them because it took too much calcium out of the bone. In fact, one of the early things we did was to develop a radioimmunoassay based on the purified hormone. We did that with Burson and Yalow, other great figures in endocrinology who won the Nobel Prize for the wonderful things they did. One of the things they did was to collaborate with Auerbach and me when I was still at NIH, going backwards a bit in time, to develop the first assay so that if a patient had a high blood calcium, you could measure whether the hormone was high. If it was, it meant they had hyperparathyroidism. So that was the paradigm at the time. When that would have been, say, in very late 60s, early 70s, osteoporosis was known to be a very troublesome disease that many patients, if they lived to be older, over 60, particularly women, would get this loss of bone mass and lead so to the state where the bones were no longer strong enough to support their weight, and they would have what are called fragility fractures. So the vertebral bodies would collapse and break, crush a bit, or they'd have a minor fall and break their hip. And it was often, particularly a hip fracture, was a life-changing event for many elderly people. They never recovered from it. But there weren't any treatments for it. And there weren't any techniques for measuring bone mass that were really very accurate, so that you didn't know you had osteoporosis necessarily until you began to break bones, and then they all would break pretty quickly, one after the other. And Parsons had noted that Albright, who had been the chief of the unit so many years earlier that I came to at MGH, had done a study in rats and showed that a daily injection of parathyroid hormone, instead of having it come up high as you would in the period of challenge of low calcium, would come up and stay much higher than the basal level and bring the calcium up with it. But if you just did a little squirty injection for a few hours, that Albright noted in rats that he was studying for another reason we didn't get into, that it built bone, didn't break it down. And he said, we should try parathyroid hormone as an agent for osteoporosis. Well, since there wasn't anything around for that, we tried it, and that story went on for many years, but it proves to be a paradigm-shifting development in which it builds bone for reasons that are paradoxical when you understand its role in biology, but which may be explained in other ways we now have some insight into. And it was a wonderful development. So parathyroid hormone moved from the calcium thermostat to a critical agent in bone health. And that's been the dominant paradigm now.
And how did that switch from paradigms? How did that dominate the field of contribute to the field of endocrinology as a whole?
Well, I think that the realization that a hormone could be used in a powerful way to stabilize bone and build it back up linked two different fields. The bone field was not much of a field back then. In fact, the American Society of Bone and Mineral Research, which is a sort of sometimes cooperating sister institution to the Endocrine Society, didn't even exist until it just celebrated its 25th anniversary. And it came into being because the success, and it wasn't just what we were doing, but others were learning how to measure bone mass non-invasively. They isolated bone cells and found out how the bone cells talk to each other in vitro, and then how to follow how that communication occurred in vivo. And as people were aging at the time, you could learn how you might be able to prevent or reverse osteoporosis, which was very important. And there were other great figures in the field, Herbert Fleisch in Switzerland, and Gideon Rodin, who was at the first laboratories here and then went to Merck, where he teamed up with Michael Rosenblatt and others. And they all developed the anti-resorptive agents. So the bone field, which would help bone to build back up by blocking its loss, parathyroid hormone would build bone up by directly driving new bone formation. All these entities drifted together, and so now, even at the Endocrine Society, there are several sessions on bone and the interplay between endocrine agents and the bone. And so the field has just moved on, as happens when the field gets lively, and that which wasn't appreciated before suddenly becomes the new paradigm. And then there'll be a change. We'll find out something else about parathyroid hormone or about bone, and it'll take another change. And good scientists are alert to that and excited by changes. Those that are a little bit too wedded to their own traditional way of thinking even sometimes resent these paradigm shifts and are slow to accept them. It's not wise, but that's what happens.
And what were the therapeutic results of this?
The therapeutic results were very, very striking. Parathyroid hormone, when given, we learned early on, to patients with osteoporosis would build bone back up. We didn't in the early days know quite how to measure this as well as we do today. Now we have methods of measuring non-invasively bone mass. And you can see the increase in the bone mass, 2 and 3% per year. In fact, parathyroid hormone will build up bone as much as 12 to 14% in 18 months' time, which is very powerful and moves you away from the fracture threshold. That's what we can say today. But we sense that we were getting a positive result back then by bone biopsies and by measuring total calcium balance, rather crude techniques compared to today. But we knew in the right direction, and our patients who had nothing else to help them were pleased to have this opportunity. And so we were able to, so now, when we did the structure and the synthesis of the molecule, it was the Harvard rule was that it had to be dedicated to the public domain. So one of the things that delayed pharmaceutical companies picking up the idea when other investigators, some of whom are members of the Endocrine Society are here, also picked up the theme begun by Parsons and our group. It happened in England and happened here. Others began to study it and excited by it, and the methods were then getting better and better to evaluate what was happening. And so there were a number of clinical investigator-initiated studies, and finally Eli Lilly Company said, we can handle this without a patent. They came in, developed the drug, and it's been approved since 2001. It's now about a little under $1 billion a year drug internationally, and it's been very, very helpful in treating patients with osteoporosis. It had some problems, but we don't need, in other words, it had some, during its development, some things happened that slowed it down. For example, there was a toxicology study that was probably much too, I would say, ill-conceived, and there was some osteosarcoma that showed up in the cancer-prone rat strain that the toxicologist chose to study and pour parathyroid hormone into. And the FDA almost didn't approve the drug, but then when they saw the great clinical benefit, they did. It still carries a black box warning, but now everyone realizes that, I think, and is comfortable with the view that to treat patients with osteoporosis, the risk-benefit ratio is very, very favorable, and the likelihood they're going to develop an osteosarcoma is very low. But that's another topic. Anyway, so it goes on, and it's been very exciting to watch it, and it's been gratifying to me.
Did you, aside from your early contribution, did you have an active role in shepherding it through from bedside to from bench to bedside?
Well, that's a very, very good question. Many people played roles there. Robert Neer is one of the lead investigators in our group who was there when I first came. So he and I and other people, David Slovic and others, worked on this together as a group through the 80s, published several papers showing that it would work both in men and in women. The methods were getting better. And then when Eli Lilly, he and I worked with Eli Lilly to get them to pick up the opportunity, encourage them to do so. And then there was a clinical advisory group that Eli Lilly put together, and I was the chair of that, and tried to help them as they were facing the practical problems. For example, encouraging them to stay the distance when the osteosarcoma appeared and the trials were halted. And I went with them to the FDA, along with others, and gave testimony about the fact that this was a beneficial drug. So I guess I've been with it all the way, but playing different roles at different times.
And are you still actively involved with parathyroid hormone therapy?
Yes, yes. I mean, I'm very interested in making a better parathyroid hormone at the basic science level, one that might work even better than the one that we now use. And
for osteoporosis?
For osteoporosis. And there are some theoretical reasons why we might be able to make a better one. We think it may be that parathyroid hormone works the way it does because it imitates a companion molecule called parathyroid hormone-related protein that we now know through the power of molecular biology goes back in time. Both of them go back to fish, parathyroid hormone-related protein, and the receptor, very early in evolution, which tells us there's more to parathyroid hormone's role than we now know, because the glands first appear in vertebrates when they move to land and have the challenge of calcium metabolism. But to come back to the point you're making, we think that a quick on and off interaction between the lock and key would be the way to make an even more effective parathyroid hormone, because what limits its effectiveness is that after about 12 to 18 months, bone resorption begins to pick up. So what you want is to build bone and not break it down. But parathyroid hormone first builds it up. My colleague John Bilezikian, who's done a great deal of work in this field, calls it the anabolic window. If you imagine bone formation going up like this, bone resorption doesn't and then begins to come up. So the gap between the two is maybe responsible for most of the gain. That's probably oversimplified. The story is much more complicated. Some people feel you need some resorption to get optimum formation. It's part of the great questions being currently addressed. But we have reason to believe that you might be able to design a molecule that wouldn't have that rise in resorption. And Andrew Stewart, who's speaking tomorrow, I think it's tomorrow, the next day here, giving the Auerbach Memorial Lecture, is going to talk about PTHRP. And he's introduced it into therapy of osteoporosis and shows that some preliminary data that suggests that it might be more effective even than parathyroid hormone, which to me makes sense because it may be what parathyroid hormone is imitating. Parathyroid hormone-related protein may be being made in the bone, and quick on and off mechanism, quicker than PTH, which really has another function. So PTH may have been imitating what PTHRP does. Given that, we think we can make a molecule that will be more like PTHRP, or even better than PTHRP in this regard. And then we've learned, this is work that Tom Gardella, Makoto Okazaki, and others in our group at the moment have gotten into. We've learned that you can go the other way. You can make a parathyroid hormone that locks, the key goes in the lock, and the whole operation goes through the door into the room and continues to work. We think that molecule, that direction, might lead to a treatment for hypoparathyroidism, a condition that affects only a small number of patients, maybe less than 200,000 in the United States. But my colleagues and I went to a meeting of the Hypoparathyroidism Association of the United States. And we were all deeply moved, this was just last week, to hear about the problems they suffer and the difficulties that are often seen when you try to treat these patients with vitamin D and high calcium intake, because parathyroid hormone has never been used in any systematic way for hypoparathyroidism. Normally in endocrinology, if you have too much of a hormone, you take out the gland that's overactive. If you have too little, you replace it with the hormone. Parathyroid hormone has never been long-acting enough to have it as a practical treatment for hypoparathyroidism. But I think it might be a good treatment, and I think we may be seeing in our very basic research a way to go that might provide a treatment for hypoparathyroidism, which of course would make my colleagues and I very, very happy if we made another medical contribution. We're working very hard on that now.
And in terms of that aspect of your research, how does this meeting, the annual meeting this year, what opportunities do you get to network about this or discuss it with? How does the meeting help you move further?
Well, I think it's an excellent question. These meetings, like that of the Endocrine Society or this so-called sister institution, the American Society of Bone and Mineral Research, are great meeting places where people from all over the country and from abroad, from both Asia and from Europe, come together, and there is a set agenda where people are invited for the program committee who has to prepare all this some time in advance. They give research talks, formal and informal, different formats. And there's great intellectual stimulation, and people ask questions, and you can see a vast sea of intellectual effort being stimulated by this meeting. And there are many sessions in this meeting on the bone field. But of course, I like to go also and listen to things that my colleagues are doing in other areas, in steroids and in reproductive endocrinology. So you get stimulation by listening to what's happening in your own field and what's happening in fields that might be not directly related, but in which you may sense another paradigm shift or a way in which people think differently about things. So it's a tremendous stimulation. This Endocrine Society has so many topics that bone is only one of them. But we will hear a lot about bone and talk a lot with our colleagues about it. I've already talked with some of my colleagues here about this idea about the long-acting parathyroid hormone. They're interested.
How do you teach paradox? How do you teach an appreciation of paradox?
Yeah, that's an excellent question. Maybe best by example, more than anything else. If something new turns up that doesn't make sense, how do you react to it? It may cause the pathway that you were thinking of going in to be turned on its head. Does that make you annoyed and you feel, oh, they didn't do the experiment right, do it over again, it's wrong? Or do you say, hey, maybe there's something here we don't understand? A certain humility toward our understanding in biology, in my mind, is important. A scientist has to be skeptical about his own findings and reproduce them very carefully, and only when he can't prove himself wrong can he think he's right. That's sort of one aspect of the scientific method. But oftentimes we're off with much broader concepts, and all of a sudden something goes the way we didn't imagine. And I love paradigm shifts and paradox, and it makes one think. And I think the sort of group that we have drawn together at the endocrine unit at the MGH, which I'm now a senior member because Henry Cronenberg is the chief, but Harold Yupner, who went with me to this parathyroid conference, patients with hypoparathyroid. When we see new things, I think there's sort of general attitude in the group, maybe we don't understand something. That could be very interesting. And it's much more interesting to discover something that's the opposite or different than what you expected, because it often signals a sudden new burst in understanding. I think that's the only way you can teach it. You can't give a lecture about how you can show by example when you're talking about what you're doing. You can show by anecdote or by responses what's happening, but you can't teach it in a didactic way, I don't think.
I'm shifting a little bit here, but in a period of tight funding, what can the Endocrine Society do to help the new emerging scientists establish their careers?
It's an excellent question, and one that the senior members of the Endocrine Society worry about a great deal. What can we do? Those who've been fortunate enough to move through our careers and are now in senior positions, sometimes they're holders of chairs or as in my case, I'm still on full-time academic salary because of the policy of the hospital. And so that's, for years of service given, there's a support, right? So I don't depend on grants for my salary support. Years ago I did. So what we are doing is using some of the resource. The Endocrine Society is really doing a remarkably good job of using the resources that it generates. It has an annual budget of about $23 million or $25 million, I believe. And it has reserves of about 18 to 20 million that have been invested. And it's very aggressively using that money and very wisely to encourage young people to enter the field, to provide fellowships, to make it possible for them to come to the meeting and see what's going on here, travel grants. The current president, Margaret Shupnik, at this luncheon we just came from, was telling us about the large number of young people that have been gathered in pediatric endocrinology, clinical endocrinology, and basic endocrinology, because there are people who are not physicians who are members of the Endocrine Society. They're PhDs. So you have streams of basic science, clinical science, and people in between who might be physicians or PhDs. And so trying to stimulate them to not be discouraged, to support them with grants is very important. The other thing the Endocrine Society does is lobby with Congress, with NIH, to keep the support level for younger people coming. And there are a lot of things that happen in NIH now. Sometimes the first award is given a better hearing. If you this is your first grant, you'll get it funded even though the priority score is lower. They want to encourage people to come into the field. And you have to look for other means of support. For example, if you can get unrestricted money from industry, if you can get philanthropy in your institution to give money, then you can use it to stabilize the young people. It's a constant problem. To the nurture, the feeding and nurture of the young is a major challenge. The institutions that, like the Endocrine Society or my own hospital or the Harvard Medical School, that really pay attention to that, are doing the right thing, most of all. But secondly, they're keeping themselves stronger, because by bringing the younger people on is how the institution renews itself, and they understand that, I think.
Well, thank you.
It's been pleasant talking with you. Thank you very much.